Another situation you can run into with Rayout's law, it's a modified version, is what do you do when you're dealing with two solutions that are volatile? And you're going to combine them together and make another, or two liquids combining together to make a solution. Both of them are volatile. So volatile just means it evaporates. It has high vapor pressure, meaning that it is going to convert itself into a gas. So you modify Rayout's law, where it's kind of like Dalton's law of partial pressure, so to speak, where it's the pressure total is equal to the pressure of A plus the pressure of B. But each one, you need to account for the mole fraction of A and the mole fraction of B. So the mole fraction of A times the pressure of A plus the mole fraction of B times the pressure of B. And that will give you the total vapor pressure of the solution. So it says it works best with ideal situations. Yeah, just like in chemistry, everything is kind of based on ideal situations with this. So here's the sample problem in the notes that we have. It says, what is the vapor pressure of a solution prepared by mixing 5.81 grams of acetone, which has a molar mass of 58.1, with 11.9 grams of chloroform, which has a molar mass of 119.0. They give you the ideal pressures, the vapor pressures in its pure form for both acetone right here and chloroform right here. So we have these two vapor pressures with this. So the first thing we got to do is we got to figure out how many moles each one of these have. So you should see in AP, you know that they are notorious for giving you numbers where you should be able to do mental math here. This is an example you do mental math. If you do 5.81 divided by 58.1, that's going to equal, you shouldn't really need to have a calculator to do this because this is going to equal 0.1 moles. So we got 0.1 moles of acetone. The other one is 11.9 divided by 119. 11.9 divided by 119 is also 0.1 of chloroform. So yeah, it is a coincidence that these are both equal to each other. And if they're both equal to each other, when I do the mole fraction, since they are the exact same, their mole fractions will be the exact same also. Because you're just going to do 0.1 divided by 0.1 plus 0.1. So that gives you a mole fraction of 0.50. Technically speaking, when you have two liquids here, whatever the difference is between one minus this number will tell you the mole fraction of the other. So if this is the mole fraction of A, the mole fraction of B, 1 minus that number will give you the exact same thing. But I'll just show it to you. So the mole fraction of B is 0.1 divided by 0.1 plus 0.1. Oops. So 0.50. So they're exactly the same with this. So we got full mole fractions of 0.50 for each one. But all of them, even if you have three liquids, all three of them need to add up to a value of 1 because mole fraction at its highest point would be 1. So now that we have these mole fractions, we're going to use each one of these and we're going to apply them to these situations with this. So if I say 0.5 times 345 plus 0.5 times 293, this is the mole fraction of A times its vapor pressure of A, the mole fraction of B times the vapor pressure of B. Combining these together, that's going to give me the overall vapor pressure of the two liquids combined together to form a solution. So in this particular one, I got 172.5 for the first one plus 146.5 for the second one. When I combine these two numbers together to get my final vapor pressure, that is going to give me an answer of 319 millimeters of mercury with the correct number sig figs, which is 3. All right. So I hope this helps you guys understand how to do Rayout's law with any of these types of calculations, and helps you kind of get through the notes with everything that you have with this. Now these are pertaining to problem set 2, as well as using the worksheet because there may be Rails law questions on the worksheet as well. So best of luck and keep doing what you guys are doing with the work, and you're doing a great job. And Mr. Brown and I definitely support all the effort that you guys are doing in this difficult time.